Okay, welcome to Easy Mathematics and a new video. Fun with polynomials, power sums of roots. Yeah, I'm sitting outside, so it can be noisy maybe, but yeah, here it's a very nice weather, so I sit outside. Yeah, what is our plan? So first, I want to explain what we want to do exactly. Then we make some exploration. Then we discuss two ways how to find these power sums, and the last point I give two examples. Alright? So, given is a polynomial p of x of degree n with rational coefficients c0 up to cn, and yeah, let's say cn is 1. So p of x is of the form sum from k equals 0 up to n ck x to the power k, and yeah, this can be written also in a factor form, k from k equals 1 up to n x minus rk, where rk are the real and complex roots. Alright? And our goal is we want to find the sum from k equals 1 to n of rk to the power n. And I note this as capital R of n. So what we want to find is the power sum of the roots of a specific polynomial. And yeah, if you like, you can write also R of p of n. So yeah, if you like. Yeah, and we want to find that for all n. In the integers, we will see, yeah, we can find also the sum of the reciprocals, for example. And I want to mention the roots are not explicitly given. Yeah, so we in general we have the summation form, not the factor form. Okay. Yeah, exploring some small examples. In the case n equals 1 is boring, you can do it by yourself. For n equals 2, we have x to the power 2 plus c1 x plus c0. And yeah, this can be written as x minus r1 times x minus r2. And if we multiply this out, we get this form, and then by comparing the coefficients, or by the theorem of Vietas, we find c0 is minus r1 plus r2, and c0 is r1 times r2. And yeah, we make a first observation: r of 0 is n for all polynomials. Yeah, you can see this by our definition. If you plug in 0, we get r to the power 0. This is 1, and we have the 1 n times, so r of 0 is n for all polynomials. Yeah, r of 1 is r1 to the power 1 plus r2 to the power 1, and this is, yeah, r1 plus r2, and this is by Vietas minus c1. Alright? For the quadratic sum, we use the binomial theorem, and we can write this as, yeah, r1 plus r2 quantity squares minus 2r1 r2, or another way of writing this is c1 squared minus 2c0. Yeah, I leave that for you. And if you play the same game for the cubic case, after some manipulation, we find minus c1 cubed plus 3 times c1 30. Okay. And we see that we can try to write these sums also in terms of the previous power sums. So for example, r2 can be written as r1 squared minus 2c0, or we can try to write r cubed and r3 in terms of the previous power sums, and we find, for example, minus r1 times r2 minus c0, and so on and so forth. And interesting is maybe the sum of the reciprocals. we find in this case R1 over C0, for example, and so on and so forth. We can play around with this stuff, maybe take a cubic polynomial and try to find some patterns. And yeah, there's of course a general solution, in this case by Newton. And the zeros, so first I want to say that the zeros are related to the coefficients via the theorem of Vieta. You know that? Yeah, for a polynomial of degree n of the form sum ck times x to the power k, if we factor out cn, then we can write this also in a factor form. And the coefficients and the roots, they are given via this formula. I called it Vieta of k. And yeah, this is this crazy looking sum. But if you know about Vieta, then this is not a big deal. If you do not know, yeah, you can check yourself the Vieta theorem. It's really obvious in my opinion. It's not so special formula. Yeah, and we define here also Vieta of 0 is 1 and Vieta of k is 0 if k is greater than n. Okay, this is a useful definition for higher power sums, as we will see. Yeah, and the Newton formulas, they're also sometimes called the Newton identities. And the power sums R, capital R, can be determined recursively. This is what Newton found. And yeah, I write this in this way. K times Vieta of k is the sum of I equals 0 up to k minus 1 of minus 1 times k minus I times Vieta of I times R of k minus I for k in between 1 and n. Okay, this is one way to write this down. On Wikipedia you find another notation. Yeah, try to pause the video and make sure both formulas are equivalent. And yeah, what is our idea? So I want to give an idea of the proof. It's not the full proof, but I just want to give an idea. We can start by summing up all the p of all the roots, and p of a root is 0 by definition. And if we sum this up, first we use the definition of p. This is the sum of ck times ri to the power k. Next, because both sums are finite, we can change the order of summation. And why we do that? Now the inner sum is not depending on k, so we can factor out the ck, okay? I want to delete the blue. I cannot take this blue part. Why? Okay, no problem. So you see, we can factor out the ck of the inner sum, okay? And now the inner sum was by definition capital R of k, and yeah, we see that if we plug in the polynomial for x, like in a formal way, and so if we write down a linear combination of the power sums with the help of the coefficients of the polynomial, we get 0, and this is the way to define it recursively, okay? This is how we get this previous result, okay? Alright, the rest is for you. You think about that. Very nice result. And yeah, a challenge for you now is show that for a polynomial with alternating signs. This is also just for formal reasons. For an alternating signs, we can write the power sum rk via this determinant. This is my first challenge for you. The power sums can be written as a determinant. Have fun with this challenge. Try it, it's funny. And another way of using series expansion, and another way is using series expansion, and for that we consider the logarithmic derivative of a polynomial, and you will see why we do this. So we use here the factor form of a polynomial, and the logarithmic derivative of a polynomial or of a general of a function is the derivative over the function. And it's a nice small exercise for you. Using the product rule, we directly get to this sum. So k from 1 up to n of 1 minus x minus rk. This is the logarithmic derivative. And now what we do, we factor out an x, 1 over x, to get this expression. And next we use the geometric series. And for convergency and so stuff, I let you guys to think about the convergency. So we use the geometric series here. The next step is quite obvious. So a fraction to the power is the power over the another power. And now here in the inner sum, the x to the power j is not depending on k, so we can factor this out. This x, it comes inside in this sum, and therefore we have the logarithmic derivative of this polynomial is this following sum: j equals 0 up to infinity of r of j over x to the power j plus 1. And like I said, for switching sums and the convergency, I let you to think about that. And this is in another way saying this is the Taylor series at x is infinity. It's also called the Lorentz series. And another way of finding this series is polynomial long division. So try it with a small example, and you will see that we will get also this result if we use polynomial long division. So without using the geometric series and taking care of the convergency and stuff like that. And then I have a small example for you with the polynomial long division with pen and paper.
So, okay, I want to show you an example, and for that we consider cubic polynomial x cubed minus 5x squared plus 9x minus 5. And we assume we have no idea about the roots, but I tell you the roots. We have 1 and a pair of complex conjugate zeros. But for a cubic polynomial, in the most cases they look really complicated, and we want to find R3. And if you do that with these roots, so the cubic is sum of the roots, we will get 65. And we calculate this sum with the polynomial long division. I just want to show you. So we need the derivative, 3x squared minus minus 10x plus 9, and we add some 0 terms and we divide that by our polynomial x cubed minus 5x plus 9x minus 5, and we see what we get. So the first step, 3x squared divided by x cubed is 3 over x. Multiplying this term through our polynomial, we have 3x cubed minus 15x plus 27 minus 15 over x. We subtract that. First term cancels out and we are left with 5x minus 18 plus 15 over x. So this term is R0, and it makes of course sense that this is 3. So our next power sum is 5x over x cubed is 5 over x squared. Multiplying this term through our polynomial, we have 5x minus 25 plus 45 over x minus 25 over x squared. We subtract that, the first term cancels out, and we are left with 7 minus 30 over x plus 25 over x squared. So the 5 is R1, and you can see that easily that, yeah, this is correct. So the next step is 7 divided by x cubed plus 7 over x cubed. Multiplying this term through our polynomial, we get 7 minus 35 over x plus 63 over x squared minus 35 over x cubed. We subtract that, first term cancels out, and we are left with 65 over x plus 38 over x squared plus 35 over x cubed. So the 7 is the quadratic sum of the roots. And the next step, you see 65 over x divided by x cubed is plus 65 over x to the power 4. And therefore 65 is our cubic sum of the roots. And if you play this game more and more, you get the higher powers of the power sum. Alright, back to the video.
Yeah, as you have seen with the polynomial long division, we get the power sums. And yeah, the second challenge for today is play the same game for minus p prime over p to find following sum. This is from j equals 0 up to infinity of r of negative j plus 1 times x to the power j. So this is the Taylor series at x equals 0, and in this time the coefficients, they give us all the reciprocals or the negative powers. Yeah, and yeah, what can you say about dj over dxj of negative p prime over p at x equals 0? I said this a couple of seconds ago. Yeah, but just think about that, and now we have a way to write down the power sums for negative exponents. Yeah. Point 5, the examples, and one example is For example, solve in the reals following system of equations. Yeah, the sum of is 6, the quadratic sum is 14, and the cubic sum is 36. And the first way, it's maybe the most natural way. Yeah, for example, we solve 1 for z and plug z in 2 and 3 to get following two equations, some polynomial equations, and then we solve 2 for example for y. We get two solutions. Here's the first one and the second one with another sign, and then we can plug in y1 in 3 and play the same game for y2, and then we get an cubic equation in x, for example, and we can try to solve this. Yeah, we get x1 is 1, x2 is 2, and x3 is 3. Yeah, this way is not so hard and difficult. It's maybe ugly. Yeah, and because of the symmetry of the problem, we conclude that another solutions are all the permutations, and they are all solutions. Yeah, like I said, so this is a very messy way. It's not difficult, but messy. If you try it, you will see what I mean. And we are interested in getting the cubic in a more easy way, and we use our result with the power sums. And what we want to find is a cubic polynomial in T with the roots x, y, and z. And how we can get this? With the Newton recursion, yeah, we find that a, our first coefficient, is the negative sum of the roots, and this is exactly the first equation. So our first coefficient is negative 6. Then the second coefficient, with the Newton recursion, we find 11, and if you play the same game with the last coefficient, we get minus 6, and this is exactly the same polynomial we found earlier, and therefore we can solve for the zeros with polynomial long division and whatever. Yeah, and this is a more elegant way if you know about the Newton identities and we have not a big mess with all the roots and solving hardcore equations. Yeah. So try this example, pause the video and try this example by yourself. You will see it's not so hard and it's very clean way. And the second example what I want to show is yeah, we have a polynomial x to the power 15 minus x to the power 2 plus 8, and obviously r1 is 0, and it turns out that r2 is 0, r3 is 0, and therefore it's a nice question. Find the smallest k greater 0 such that r of k is not 0. What is the smallest positive k that the power sum is not 0? Pause the video and try this by yourself. Yeah, we use polynomial long division as we have seen, and first we need the derivative of this function. This is 15x to the power 14 minus 2x, and now we make polynomial long division. 15x to the 14 divided by x to the 15 is 15x to the negative 1. Multiplying this with the denominator, we find this expression, and now we subtract 13x minus 120x to the power negative 1. We play the same game with polynomial long division, and now we get the first coefficient 13x to the negative 14, and therefore we have x of 0, r of 0 is 15 and r of 13 is 13, and therefore the smallest k for which the positive exponent is not 0 is k equals 13, pardon. Yeah, and that's all for today. Have fun with the power roots. Enjoy. See you next time. Bye bye.